So the next thing we're going to think about with vectors is what the magnitude of a vector is. And when we talk about the magnitude of a vector, we've probably come across this word before, but the magnitude of a vector is actually its length, okay? The way that we denote the magnitude of something is we put these two lines around the outside of this. So remember, if this was being typed, apologies, if this was being written, I would write it with an underlining over it. But these two lines that go either side of that vector are telling me to find out the length of that line, the length of that vector. So I've got an example here, which is the vector A to B, which I've written like this. And the vector is 3, 4, which means that it is moving 3 spaces to the right and 4 spaces upwards. And if I want to find out the length, I actually just want to know what's that measurement between A and B. So the type of maths I'll be using is Pythagoras, exactly. So you can see how Pythagoras is just going to pop up in lots and lots of places. So the length AB here would just be the square root of 3 squared plus 4 squared, which we know is that Pythagorean triple, the 3, 4, 5, 1. So the length of the vector AB, the magnitude of the vector AB is 5. So you can see in my notes here, I've said that if the vector A is xy, then to find out the magnitude of that vector, you would just do the x squared and the y squared and square root it. Do you remember when did we last use that formula? What topic did we use that formula in before? The distance between two coordinates. And do you remember we avoided doing the negative being squared? We just found it easier just to write these bits being squared without the negative, just in case we made any slip-ups with it. So even in this one that I've got here, where I've got 1 minus 1, meaning it's going 1 across and 1 down, what would that be as the magnitude?
1 squared.
Yeah, 1 squared plus 1 squared. We don't have to worry about the negative, which is just the square root of 2. So the length of the vector 1 minus 1 is just root 2. And root 2 is roughly 1.41. Okay, so it's about 1.41 units long, okay? You can notice here the reason I included this example is to show you that you can put the modulus lines, these are called modulus lines, that we'll use that term a bit more in the future. You can put these magnitude lines around a vector in column vector form. It doesn't just have to be in this form like this, the arrow form, or in the vector form like this. It can be written around anything to get the magnitude. And so what would the magnitude of this vector, minus 5, minus 12, going 5 across and 12 down be? Yep. 5 squared plus 12 squared, and that is 13, because there's a 5, 12, 13 is a triple that will always work together as well, okay? So very quickly, just fill these two in as well at the bottom of the page. Okay, so this first one, we should have had the square root of 4 squared plus 1 squared, which is just root 17. And what about the second one? It's just 2. There's no point in doing any Pythagoras to that because it's clearly just going 2 units to the right. So not everything, because we have a formula, not everything requires the formula. You need to be careful and think about what it's actually talking about in order to answer that question in the most efficient, most useful way of answering that kind of question, okay? So we're now going to talk about something that is linked to the magnitude of a vector, which is finding a unit vector instead. Now, when we hear the word unit, what does unit make us think of? 1. It makes us think of 1, okay? So we're talking about vectors that have to have something to do with 1. And it says here that a unit vector is a vector whose magnitude is 1. Okay, so in the previous questions, we came up with vectors that had length 5, root 17, 2, and things like that. But we're going to want to try and find out what a unit vector is. And the reason we do that is because there are certain operations on vectors that require the vectors to be unit vectors. So I can't quite go into the reasons of why we need this, but I'm just giving you some skills that we will use for the future, is that sometimes we need to know what a unit vector is. And the way that we do this is we just scale the vector so that its magnitude is now 1. So I'm going to do it with this example here, and then we're going to try and explain why this thing I've got written in the orange box is true. So this vector that I've got here is 3 spaces across. So 1, 2, 3 spaces across, and 1, 2, 3, 4 spaces up. So this vector that we've got here is the vector A. It's 3 across and 4 up. So the length of this line from here to here, we have just worked out on the previous slide, is 5. But I don't want it to have a length of 5. I want to reduce it so that it has a length of 1. Now I'm just going to take this and split this up into the 5 pieces, if I can do that carefully. So I just want to know, what is this vector that I've got here? I want it to be in the same direction, but I want it to just be a fifth of the original length. I don't want it to go all the way up to 5. So how do you think I would describe what this vector here is going to be? Yeah. Yeah, it's like a ratio kind of thing. Okay, so these are in a ratio of 3 and 4. So what do you think how am I going to describe how much across am I going to go, do you think? Pardon? I heard 2 people at the same time. Prophet, what did you say? Yeah, if I'm going across 3 for the whole thing, and I'm now only doing it up a fifth of the whole, because it's a similar triangle, this bit is going to be 3 over 5 across, meaning that the bit going up would be 4 over 5, okay? That's because what we've got here is a little triangle and a big triangle. The big triangle is the one that we drew in blue, that is 3, 4, 5. Because they are similar triangles, that means that they have been scaled up by the same amount. So if this one is 1, to go from 5 to 1, I divided by 5. So that must mean to go from 4 to this side, I must also divide by 5. And to go from 3 to this side, I must also, whoops, that doesn't quite look like a 3, I must also divide by 5. And this is going to be a unit vector. So the unit vector for this one that we've got here, which we draw like this, we do A, and then we put this little hat on it. It's called a circumflex. The unit vector A is going to be 3/5, 4/5. Okay? And I'm just going to prove something to you. If I was to do the magnitude of the unit vector A, it would be the square root of 3/5 squared plus 4/5 squared. 3/5 squared is 9/25. 4/5 squared is 16/25. So that's the square root of 25 over 25, which is the square root of 1, which is 1. So it does have a magnitude of 1, okay? So I've just proved that it does have a magnitude of 1. You may sometimes write unit vectors. If you don't want to put the fifth inside, you could put the fifth on the outside like this, and you could just be multiplying 3, 4 by 1/5. It's just an aesthetic thing. It depends which one you prefer the look of. One of them has got the fifth inside, has been multiplied by the scalar. The other one has got the fifth on the outside, where the scalar multiplication is removed from it. It's to the left. And so hopefully this now makes a bit more sense. It says, if A is a vector, then the unit vector A hat, or sorry, not A hat, I do sometimes call it A hat, but the unit vector A with this hat on the top of it, in the same direction, is the unit vector is equal to the vector A divided by the modulus of that vector. And this isn't perhaps the best way of writing this. I would probably like you to write this as it's 1 divided by the magnitude multiplied by the vector. And that's a bit easier to see here. We've got 1 divided by its magnitude multiplied by the previous vector that we've got. This is the geometry of why it works. We're taking the long vector and we are scaling it down by dividing by its length so that it's going in the right direction. Yeah, Jamil?
So it's the original A, the modulus.
The original A, this modulus here is the modulus of the original vector. Because if it was the modulus of the unit vector, it would just be 1 anyway, okay? So why don't you just have a go at trying these two that we've got here? If you're not sure, I'm going to talk about them in a minute and a half anyway. So just read through the top bit. If you're not sure, read through what we did on the top half again, and then we'll go through these in just a minute or two, okay? Okay, you haven't quite had a go at them. We'll just talk about these two as we go. So I'm going to try and do this without drawing the diagram to begin with. I'm just going to try and use this version of the formula that the unit vector A is going to be 1 divided by the magnitude of it multiplied by the vector that we've got. So I need to know what the magnitude of this. What is the magnitude of this vector? 13. It's a 5, 12, 13. So my unit vector is simply going to be 1 over 13, 12 minus 5. And you could have written your answer like that, or alternatively, you could have written 12 over 13 minus 5 over 13. Either of these answers would be correct.
Do you have to put the minus in there?
You do have to have the minus in there, because if it didn't have the minus in there, it wouldn't be going in the same direction. It wouldn't be the same vector. They need to be going in the same direction, but just with a length of 1.
So it's only for the squaring then?
Yes, it was only for the process of squaring that we can ignore that negative just to make our calculations easier.
So we have to underline the A.
Yes, I want you to underline the A, because if it's this implies it's going to be equal to a scalar. This implies it's going to be equal to a vector. And they're talking about different kinds of things. So if you can try and get into the habit of actually writing them in that way, I suppose the thing that's confusing is when I type them, I don't underline them, because when they're typed, they're bold. When you write them, you underline them. And for B, we're going to do the same thing. So the magnitude of B, Khadija, what's the magnitude of this one? It's just root 2. So what did you get as the unit vector B? 1 over root 2 multiplied by 1, 1.
So would that just be the final answer?
You could just give that as your final answer. If we wanted to do some further manipulation to this, there's probably 2 things we could do. Can anyone suggest one of the 2 things that we could do here if we wanted to do some further manipulation? Jamil? Good. One of the things we could do is rationalize the denominator. What is 1 over root 2 rationalized? It's root 2 over 2. So this is one of the things I could do. What do you think is another thing I could do?
Times by 1.
Good. I could also put this scalar inside the vector. So I could say it's root 2 over 2, root 2 over 2. So these 3 things that I've got written here all show the same thing. And what they actually show is if this is the vector B, which is going 1 along, gosh, that's not very neatly drawn, 1 along and 1 up. This is 1 and 1. People often think that this length is 1 as well, like when you're back in like primary school. But obviously this isn't 1 long. This is root 2 long. So the vector would actually be that we've just described, perhaps that amount of the line, so that it's the same length as this one. So this is the unit vector B, and the longer one is the vector B. We've shrunk it down so that it's just got a length of 1. And for now, we're just going to see this as like a standalone skill. It does get used, probably not for a while. It's just going to be seen as a standalone skill for a bit. If you go and do anything with engineering, it's the kind of thing that you would be using in engineering at university as well, and it will also pop up in some things with further maths as well. So that's all I'm going to say about unit vectors. My advice is either to try and think logically how this works. If you're that kind of person that likes to know how everything works logically, then that for me just makes sense with unit vectors. If you're someone who would just like to have like something to memorize, then you should memorize that a unit vector is this thing here. You know, you created some notes of your previous chapters for me for one of the homeworks. This is the kind of thing that should go into your notes for vectors, because it's something that when I do exams at the end of the year, it's something people always forget because it's such a small thing. We've spent like 5 minutes on this, but it will come up. Okay, so make sure when you're going through your notes, this is something that you put in, and I'd like it if you can understand it, but if not, make sure it's something that is memorized. Okay, so we're going to do some more bits before we do some practice. We're now going to try and learn more about vectors, more ways of describing them. This time we're going to try and describe the direction of vectors, okay? So this time the question asks, find the angle between A and the positive x-axis. So the vector that we're talking about here is the vector 4, 5. And the best thing that you should always do for any of these direction questions is you must sketch the vector or the vectors. I'm going to put, it could be vector or vectors, because they might ask you to find the angle between 2 vectors. Or they might ask you, in this case, to find the angle between a vector and something else. Okay? So, to begin with for these questions, I always want you to start start your sketch with a dot or just something to show where you're starting your vector from. So this is where I'm going to start my vector from. And 4, 5, let me just move my dot so it's a bit lower down. 4, 5 means what in terms of directions? How do you describe that? Good. So 4 to the right and 5 up. So this is the vector A that I have here. And I'm just going to jot down and label this as 4 and this is 5. And then from the same dot, the same starting dot, I'm going to draw the second thing, which is the positive x-axis. So if this was the origin, the positive x-axis is going to be this line that I've got here. Okay? So I have drawn these two things. I have drawn the vector A, which I'm doing in orange, and I have got the positive x-axis, which I've highlighted here in yellow. Because there's lots of different ways that people could get confused with drawing these. I've seen some people draw them where they've drawn A like this, and then they've drawn the positive x-axis like this, and they find this angle. But that's because they didn't start both of them from the dot that we should draw at the beginning. So we need to make sure we're all speaking the same language when we do these questions, which is why we're going to start each of them with a dot to help us draw them. Because obviously this angle is not going to be the same as this angle here, which is the one I want to find. Okay? So I'm going to erase this one for a second. And I'm just going to give this angle a name. I'm going to call it theta. And do we know anything about this angle at the bottom here?
90.
It's 90 because we know that these two, I and J, the ones in the I and J directions, are perpendicular to each other. So if it helps you, and for some people it does help them, you could draw that triangle again, and you could put your angle in with 4 and 5. So how are you going to find out the value of that angle? SOHCAHTOA, good. So with SOHCAHTOA, which one's it going to be, SOHCA or TOA? TOA. So we get tan theta is the opposite divided by the adjacent, 5 over 4. So we're going to do inverse tan of 5 over 4. And we're just going to give our answer to one decimal place. And that's 51.3 degrees. And I think we could give a little bit more detail to this answer. It says find the angle between A and the positive x-axis. And I've said it's 51.3 degrees. Now, you don't have to write this bit down because I just want you to think about this. If this was the positive x-axis and this was the origin, and I said, okay, I want you to imagine the vector is 51 degrees from that line. What might be the problem if I just said, oh, it's 51 degrees from that line?
You could do n for it.
What was that? It could be above or below. It could have been this vector, where there's 51.3 degrees, or it could have been this vector, which is 51.3 degrees. So what do you think I should say at the end of this? I think I should say 51.3 degrees above the axis. And I don't like the textbook. They often just give you the answer. I want you to be a little bit more detailed than that and say it's above the axis, it's below the axis. Pardon?
Can you just write above and below, just write the whole thing?
Come on, it's only 2 extra words.
Yeah, no, but they could save time. If you got like 3 of them questions.
Maybe I would like you to write this clearly. I want the communication to be absolute perfect. I don't want it to be like, yeah, it's okay. I'd rather it always be as perfect as we could be. So we want to say 51.3 degrees above the axis because it could have been in these 2 different places. So we're not going to do the whole of this other question. I'm just going to make up another question just to put in this little bit here. This time I might say something that the vector B is -3, -2. And I want to find the angle with the y-axis. Okay, I'm asking a different kind of question in this one. And in fact, I might say the positive y-axis, because that's what it says here, with the positive y-axis. So we're not going to actually work out the angle, we're just going to draw the diagram. So first thing I wanted us to do is to start the sketch with a dot. And -3 is going -3 to the left and 2 down. So this is the vector b. Now the positive y-axis, you start from the dot again. Y-axis goes like this. So the angle that they want is a little bit different here. It's actually this whole angle from the north line or the y line all the way around to this bit here. So what you would do is calculate this red angle and then just add 90 degrees onto it. Okay, so that little red angle we would work out from the fact that it has gone 3 to the left and 2 down. Work out that angle using trigonometry, add on 90 degrees, and probably we should say whether it is to the left or to the right, or we might say anti-clockwise or clockwise, just to give that a bit more information. And there are other things they might ask for you to work out the angles between. So far, we've looked at an example with the positive x-axis and the positive y-axis. But in this next question, they're going to ask you to do things with vectors, with other vectors as well. Okay? So let's have a look at this second example that we've got here, and then we're going to do a chunk of practice. This second question says that vector A has a magnitude 10 and makes an angle of 30 degrees with J. Find A in terms of I, J, and column vector format. So I'm going to start off by drawing the thing that I know. I'm going to draw the J vector. And the J vector looks like what? What is the J vector looking like? It's just in the y-axis, okay? So I'm going to start with my dot, and I'm going to draw just the J vector. I'm not bothered about labeling it J. I'm just wanting to draw it on there. It's basically the y-axis. It's another way of them saying that. And they've said it's got a magnitude of 10 and makes an angle of 30 degrees with it. Now, I think there's not quite enough information here. I think they should have said it makes an angle of 30 degrees to the right or to the left, okay? So for our example, we're just going to say it's 30 degrees, like going around the clock, clockwise. So I'm going to draw this vector, which is going to be vector A, and it needs to be 10 long, and it's making an angle of 30 degrees like this. So we've kind of been given the answers. This time we're trying to say what was the question, what was the vector. So I need to, for this vector, from its starting point, I need to find out how much across it's going, and I need to find out how much up it is going. And this is going to be trigonometry again, okay? Because what I've got here is a triangle, which I'm going to redraw to make it a little bit easier to see what's going on. I can either call this one 60 or I can call the top one 30, because these are, what are these angles called? Alternate angles. Very good, Amina. These are alternate angles. Or I could call this one down here. Does anyone know why this one is 60? What the reason is? So there's a posh word for saying because it makes 90, because it's a right angle. It's called, 30 and the 60 are called complementary angles. And complementary doesn't mean like, yeah, they make, well, when we say if two angles in maths, if the two angles are complementary, it's not the same as the word complement. They're spelt differently, because a compliment, if there's an I there, it's like, oh, wow, you look so nice today. But if it's a compliment with an E, it means this. Yeah, it's more like they complete each other in that kind of way. So complementary angles add to 90. But you don't need this in today's lesson, but I will use that word complementary in... Pardon? No, you don't need to for A-level. You don't need to write all the reasons for this stuff, okay? So we can either use 60. Which one would you prefer to use, the 60 or the 30? I don't mind. You want to use the 60? Okay, let's use the 60. And this is the 10 that we've got here. So I'm going to call this bit X and this bit Y, and we're going to use trigonometry to find out what X and Y are. So X and the 10. What are the X and the 10 in turn? Am I going to use SO, CA, or TOA for the X and the 10? No, not TOA. CA, because I've got the adjacent and I've got the hypotenuse. So I'm going to start off by saying that cos 60 is equal to X divided by 10. This is the cosine of the angle is the adjacent divided by the hypotenuse. So when I rearrange this, what is X equal to?
10 times cos 60.
10 times cos 60. And then the other one is going to be that the sine of 60 is the opposite divided by the hypotenuse, which is y divided by 10. So y is 10 sine 60. And you can put these into your calculator, But this one is going to give you 5 when you put it in your calculator, because I know that cosine of 60 is a half. You should have known that from GCSE, but you had a bit of a different GCSE journey. Yeah. GCSEs, what's that? And sine of 60 is root 3 over 2. So this one is actually 5 root 3. But again, you could just put it in your calculator, and you can see that your calculator would give you these.
8.66.
Pardon?
8.66.
Yeah, but I'm happy to leave this one as 5 root 3. I'm happy to leave it as this. And for those of you who are going to want to be aiming for top grades, for A's, A stars, or who are doing further maths or anything, there's short ways of finding out when you have a hypotenuse is 10 and you want to split it into these two. This one is running adjacent, and adjacent should make you think of which out of sine or cos? Cos, yeah, because cos is the adjacent over the hypotenuse. So look, x is just equal to the hypotenuse cos of the angle. And y, which is opposite the 60, opposite goes with sine, so it's just the hypotenuse sine of the angle. And so there's some like short ways of, in the future, this property of breaking something down into these two things, you'll get used to be able to do that without having to write out these first lines. You'll go straight into hypotenuse and then cosine if it's adjacent, or hypotenuse sine if it's opposite. Okay, and you just put those things in your calculator. So there's going to be various questions that you'll be doing that I've selected from exercise 11C. I thought I might just throw in one kind of random question at the bottom for us to think about, that if I was going to ask to find, I don't know, find, and you might not want to write this down, you might just want to think about it. If it said find the angle between, let's have a think, I don't know, 2, 3 and 4 minus 3. Anyone got any suggestions about how you might even try and find the angle between two vectors? What did we do for the other? We're going to draw the triangles. Do you remember how we started off? We drew a dot. So I'm going to draw the dot, and I'm going to draw 2, 3. So I'm going to draw something going 2 across and 3 up. So that's one of the vectors. And then I've got 4 across and 3 down. So I'm going to go 4 across, and 3 down.
What would you do from the same point?
So how do you think I could find the angle that is in between those two vectors? Andrew?
You could find the angle,
I could find this one with the x-axis. I could find this one, beta, with the x-axis. And then I could add them together to find out the angle between the two vectors. Because I think I've got in one of these questions that I'm going to ask you, I want you to find the angle between two vectors. So break that problem down. Find it between something horizontal or something vertical, depending on what the diagram looks like, and then put those angles together so that the angle between them is going to be alpha plus beta, those two angles combined. Okay? Any questions on this before we launch? There's going to be some things on the magnitude of the vector, the unit vector, and the angles between vectors and I and j or x and y axis. Obviously, you can ask me questions during the exercise as well. Okay.